When you look around you at everything, really, from the stars to the screen you're listening on, it's all just matter.
Right. And we have this simple definition, anything with mass that takes up space.
But that's where the simplicity ends. The really fascinating part is what those tiny particles are doing, sort of their secret life.
That's where all the complexity is. We think we know matter because we see solids, liquids, and gases every day. But the difference between a block of ice and the steam coming off a kettle isn't what they're made of. It's all about the invisible forces acting between their particles.
So for our deep dive today, that's exactly what we're going to unpack, the invisible mechanics of the physical world.
We'll start with the particles themselves, then get into how states actually change. And that hidden energy, latent heat, is key.
And then we're going to venture into the really exotic stuff, the states of matter that are a little more extreme than what you'd find in your kitchen.
Okay, so let's start really small. At the particle level, the first thing to get your head around is that even in a solid object, those particles aren't perfectly jammed together.
No, not at all. There's actually space between them. It seems counterintuitive when you say, knock on a wooden table.
It feels completely solid.
Exactly, but you can actually demonstrate this pretty easily.
Right, the classic sugar and water experiment. You add a spoonful of sugar to a glass of water, stir it, and the water level barely moves.
It should go up, shouldn't it? You've added more stuff.
You'd think so.
But it doesn't, because the sugar molecules are so tiny, they're actually slipping into the pre-existing gaps between the water molecules.
So they're not displacing the water, they're just filling in the blanks.
Precisely. And speaking of tiny, the scale is just dizzying. There's this great demonstration with potassium permanganate.
Oh, the purple crystals? Yes. You take just a few tiny crystals and dissolve them. The water turns a deep purple.
Okay.
Then you take a drop of that water and put it in a fresh beaker of clean water, and it still turns pink. You can do this again and again and again.
And even after diluting it multiple times, you still see the color.
Which proves that those original few crystals must have contained millions, maybe billions of particles that just keep dividing and spreading out. It's incredible.
Okay, so we have incredibly small particles with space between them. The second big characteristic is that they are never, ever still.
Never. They are in constant random motion. They possess kinetic energy.
Which we perceive as temperature.
And that motion is what drives diffusion, the spontaneous mixing of different substances.
I think everyone has a gut feeling for this one. The smell of hot, sizzling food travels across a room way faster than the smell of, say, a cold sandwich.
This is a perfect example. Heating the food is literally giving those aroma particles more kinetic energy.
So they're moving faster.
Much faster. They zip through the air, collide with air molecules, and reach your nose in a fraction of the time. The cold food particles are just lazier. Their journey is a lot slower.
It makes perfect sense. Okay, so if they're always moving and have all this space, what stops everything from just flying apart?
Ah, that is the third piece of the puzzle. Attraction.
The interparticle force.
Yes, and the strength of that force is what defines everything. It's why you can wave your hand through the air with no effort.
But feel resistance moving it through water.
And you definitely can't push your hand through an iron nail.
Right.
That range of forces, from almost zero in the air to immense in the iron, that's the entire basis for our classical states of matter. So let's build on that. We can stop thinking about solids, liquids, and gases as just definitions and start thinking about them as different outcomes of that tension between motion and attraction.
A constant tug of war.
Exactly. With solids, like that iron nail, attraction wins by a lot.
The interparticle force is at its maximum.
Which locks the particles into a rigid lattice structure. They can't go anywhere. All they can do is sort of vibrate in place.
Which is why solids have a fixed shape and volume. You can't really compress them.
Right. They have minimum kinetic energy. Now, liquids are the middle ground.
Attraction is still strong enough to keep the particles together, which is why they have a fixed volume.
But the particles have enough kinetic energy to slide past each other. They can break and reform bonds constantly.
And that's what we call fluidity, right? The ability to flow and take the shape of a container.
That's it, exactly. And then you get to gases, where kinetic energy completely dominates.
Motion wins the tug of war.
Decisively. The attraction is negligible. The particles are just moving at high speed, randomly, in all directions.
Which is why they have no fixed shape or volume, and it also explains compressibility.
Absolutely. The space between gas particles is huge compared to the particles themselves, so you can squeeze them together really easily. That's how we get LPG or CNG into a tank.
And when you contain a gas, that feeling of pressure It's not a static thing, is it?
No, it's completely dynamic. The pressure on the walls of a tire is the result of billions upon billions of those high-speed gas particles constantly smacking into it.
It's the average force of all those collisions.
Mm-hmm. Now, speaking of properties, let's talk density. Usually solids are the densest.
But there's one huge world-changing exception: water,
Ice floats.
which is an anomaly. Most things get denser when they freeze. But water molecules, when they form ice, arrange themselves into this very open, cage-like crystal structure.
And that structure has a lot of empty space built into it.
A huge amount.
Yeah.
Which makes ice less dense than liquid water.
And thank goodness for that. If ice sank, lakes and oceans would freeze solid from the bottom up.
And life as we know it probably wouldn't exist. It's a tiny structural detail with planetary consequences.
So if changing state is all about that tug of war, then the way we influence it is by adding or removing energy.
Usually in the form of heat, you change the temperature. Let's take a piece of ice. You add heat, and the energy makes its particles vibrate faster and faster.
They gain kinetic energy. Eventually, they vibrate so violently that they break free from that rigid lattice structure.
And it melts. It becomes a liquid. That temperature is the melting zero point 0 degrees Celsius, or 273 Kelvin for water.
Right. And you keep adding heat, the liquid particles move faster, and eventually they gain enough energy to escape the liquid entirely and become a gas. That's boiling.
Which, for water, is at 100 degrees Celsius, or 373 Kelvin.
And boiling is what we call a bulk phenomenon. It's not just happening at the surface. Bubbles form throughout the entire liquid.
Okay, but here's the part that I always found a little bit weird. If you put a thermometer in a pot of melting ice, it stays at exactly 0 degrees until all the ice is gone.
Mm-hmm.
And the same thing with boiling water. It stays at 100 degrees even though you keep pumping heat into it. Where is that energy going?
That is the crucial question. It's going to what we call latent heat, or hidden heat.
Hidden heat, I like that.
The energy isn't being used to make the particles move faster, which is what temperature measures. It's being used to do work. Specifically, the work of breaking the bonds holding the particles in their current state.
So it's the energy cost of the phase change itself.
Exactly. There's the latent heat of fusion, to go from solid to liquid, and the latent heat of vaporization, to go from liquid to gas.
And understanding this has some really serious real-world implications.
Oh, absolutely. Think about steam at 100 degrees versus boiling water at 100 degrees.
Same temperature.
But the steam will give you a far, far worse burn.
Why?
Because each one of those steam particles is carrying that extra packet of energy, the latent heat of vaporization. When it hits your cooler skin, it condenses back to liquid and releases that massive burst of hidden energy all at once.
Wow. And the same logic applies to cooling, but in reverse.
Right. Ice at 0 degrees is a much better coolant than water at 0 degrees, because as the ice melts, it has to suck a large amount of latent heat out of your drink to make the phase change happen. It's an energy sponge.
Now, what about the states that skip the middleman? Sublimation.
Right, going directly from a solid to a gas. Like dry ice, which is solid carbon dioxide.
You never see liquid dry ice.
Not at normal atmospheric pressure. It just can't exist as a liquid under these conditions, so it turns straight into a gas. It's a great reminder that pressure is just as important as temperature in determining what state matter is in.
Okay, so boiling happens at a specific temperature. But water left in a glass will eventually disappear, even at room temperature. That's evaporation, right?
Correct. Evaporation is the quieter, slower version. It's the change from liquid to vapor that happens below the boiling point.
And it's a surface phenomenon, not a bulk one.
Exactly. Think of it as a particle escape plan.
Yeah.
The particles with the highest kinetic energy, if they happen to be near the surface, can just break free from the attraction of their neighbors and escape into the air.
And the speed of that escape depends on a few things. First, surface area.
More surface area, more opportunities to escape. It's why you can cool hot tea faster by pouring it into a wide saucer.
Right. Then there's temperature hotter means faster. And wind speed.
Yeah, a windy day dries clothes faster because the wind blows away the vapor that's just escaped, clearing the air for more to follow.
And the last one is humidity, which works the other way around.
Yes. If the air is already full of water vapor, it's harder for more to join the party. So high humidity slows evaporation way down.
But the coolest thing about evaporation, literally, is the cooling effect. How does that work?
It comes back to that stolen energy. For those surface particles to make their escape, they need a final burst of energy.
And they take it from their surroundings.
They steal it from the liquid left behind, or the surface it's on. And that theft of energy is what makes the surroundings cooler.
That's the principle behind so many things. Putting acetone or perfume on your hand feels cold because it evaporates so quickly, pulling heat from your skin.
Or traditional Indian water pots, the matkas. Water seeps through tiny pores to the outside surface and evaporates, and the heat it absorbs to do that is drawn from the water inside, keeping it cool.
And it's why we wear cotton in the summer.
Of course. Cotton is great at absorbing sweat and spreading it over a huge surface area. This maximizes evaporation, which pulls heat away from your body and keeps you cool. It's nature's air conditioning.
For most of history, that was pretty much it. Solid, liquid, gas. End of story.
But the universe is a lot weirder and more extreme than that. We now talk about 7 states, maybe more.
So let's touch on the two most different ones, the highest energy and the lowest energy states.
Let's start with the most common state of matter in the visible universe,
Plasma.
the 4th state.
Right. If you take a gas and you just keep heating it to thousands or millions of degrees, the collisions between atoms become so violent
That the electrons are literally ripped away from the atoms.
Exactly. So you no longer have neutral atoms. You have this superheated, ionized soup of positively charged nuclei and free-floating electrons.
And that's what stars are made of.
The sun, all the stars, lightning, the arc from a welder. It's all plasma. And because it's charged, it responds to electromagnetic fields, which makes it behave in all sorts of complex ways. Okay, so that's the high-energy extreme. What about the other end of the spectrum?
We go all the way down to what some call the 0 state of matter, the Bose-Einstein condensate, or BEC.
This is something else entirely.
It is. This is a state you get at temperatures just fractions of a degree above absolute zero. We're talking nanokelvins, almost as cold as it's possible to get.
So at that point, the particles are barely moving at all.
They're almost static. And when they get that cold, something amazing from quantum mechanics takes over.
Which is?
Their individual quantum waves start to overlap. They effectively stop acting like individual particles and merge into a single collective quantum entity.
A superatom.
People call it that, yeah. They lose their individual identities and behave as one. It's a macroscopic display of quantum reality, achieved by removing almost all kinetic energy from a system.
So we've gone from the idea that matter is made of tiny moving particles,
Through how their motion and attraction define solids, liquids, and gases.
and we looked at how that hidden factor, latent heat, governs the change between them.
And then we jumped from the super-energetic plasma that fills the cosmos to the quantum stillness of a BEC.
It really shows that everything we see is just the result of a microscopic battle between forces holding things together and energy trying to tear them apart.
It's a constant dance.
And that idea of the Bose-Einstein condensate as a 0 state, it's really something to think about. If heat is kinetic energy and we can strip almost all of it away, what does that say about motion itself? It makes you wonder if motion is just a property that emerges from heat, and at the absolute limit of cold, the world stops being about individual things moving and becomes about one single, unified quantum reality. Something to mull over next time you watch steam rise from a kettle.